Hey guys, how's it going? Good, good. All right, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Last week before spring break, so it's I know this is always the hardest week to do. I mean, I guess finals week is always really hard too, but you know, the week that we have right before we go on a long break is, I think, the hardest to focus and the hardest to you know, even just kind of come to class. And so, you know, I appreciate you guys being here. You know, I've lectured to empty rooms before. I've lectured in my apartment when I'm literally talking to no one but my cat. But you know, it always helps to have people here to talk to. So thank you guys for coming. Okay, so our plan for today is we're going to continue on with our lecture notes on the 1D equations. And so we got about halfway through the derivation. And so we're going to finish that up today. And we're going to see how that's applied as well. And so there's going to be a little bit of MATLAB today. Nothing that you guys have to do, but I do have a script that I want to show you that shows the 1D equations in action. Okay. All right, and so I think that's it for the plan. So I spent a good amount of time yesterday getting the image data out to everyone, and so hopefully you guys got an email from me with the Dropbox link. Unfortunately, the files are a little bit too big for me to transfer through email, and so you know, I just made separate Dropbox folders for everyone, and I sent you the information. And so if you did not get an email from me about your image data, just please let me know. I know there were a couple people that didn't fill out the poll, and so I thought I sent you a message over Canvas as well. But if you don't have your image data for your final project, you know, please let me know as soon as possible, because it's good to it would be good to have. Okay? I was pleasantly surprised, and so we're actually going to have a pretty good variety in the final project. And so you know, there's everyone kind of picked, you know, kind of everything almost equally. So you know, I'm excited for what you guys are going to do for the final projects. Okay. Okay. And so I think that's it for my announcements. So are there any questions I can answer before we get started? Oh, the tutorial. So I apologize. I am a bit behind in grading those things, but I do plan on grading them this week. So you should have your scores for this investment tutorial, you know, before the end of the week for sure. Okay. Okay. All right. So let's go ahead and continue. And what we were doing last Thursday was we were talking about the 1D equations of blood flow. Okay. And so the 1D equations are, you know, these are kind of a step up in complexity, and a step up in detail from our lump parameter models, right? And what they allow us to do is that they allow us to solve for the flow rate and the cross-sectional area primarily in a vessel along its center line. Okay? Flow rate, area, and pressure as well. Okay. And so, you know, we have a vessel that looks like this. Okay. It might be following some kind of winding path. And then along that vessel, we have its centerline path that we can trace just like that. Okay. So just like you did in Synvascular. And so from this, you know, if we solve the equations properly, you know, we should have two graphs. Okay. Right. And so remember, we call the direction along the center line, we call that the z direction. And so we should get a graph where z is on the x-axis. Okay. And then q is on the you know, on the y-axis. And so, you know, we might get something that looks like this. Okay. And we're getting a similar graph with the area. So the area might look something like this. Okay. These are just kind of examples, but you know, what I wanted to illustrate here was the kind of the types of the graphs that you're going to get. Okay, so you're going to have on one axis, you're going to have the center line coordinate for the vessel, and on the y-axis, you're going to have the quantity of interest. Okay. And the nice thing about this is that, you know, the fact that we can get solutions at many different values of z means that this has a much greater spatial resolution than our lump parameter models. Okay. And that's a good thing because, the more spatial resolution you have, the more likely you are going to be accurate in terms of your solution, that you're computing. Okay. One parameter models are great. They're a great first step, but they are very limited in terms of what you can actually do with them practically. And so 1D equations, I think, kind of is the first, big leap that you can take, where you can have very sophisticated, 1D models of blood flow. Okay. And the way, and then what we were going over at the end of Thursday was we were talking about how we can actually derive these. Okay. And so the way that the 1D equations of blood flow are derived is that you take the Navier-Stokes equations, right? You take your Navier-Stokes equations and then you integrate them across the cross-sectional area. Okay. Or in other words, we're going to take our equations and perform the following integral. And so we're going to perform an integral where we take 2 pi, we integrate from 0 to the outer radius of the vessel. Okay. And here we're going to have, whatever term that is in our equation, and we integrate it with respect to r dr. Okay. Right. And so we were kind of in the middle of this. And so we were kind of in the middle of taking our Navier-Stokes equations and integrating them, according to this criteria. Okay. But we did get done integrating the conservation of mass. And so the conservation of mass, if you recall, let me bring it back up here. Okay. The conservation of mass is given by the equation 1 over r partial r of r u r, okay, plus partial uz partial z equals 0. Okay. So after we applied this this methodology where we integrate this with respect to r, we end up with the following equation. And so we have partial a partial t plus partial q partial z is equal to 0. Okay. And so the equation on the right is what we obtained by integrating our conservation of mass across the cross section. Okay. And so we were able to finish that, but we were kind of right in the middle of doing the same thing for the momentum equation. Okay, so this was just kind of a recap from last time, kind of what the purpose of these 1D equations are, and the process that we're going through to obtain their equations. Okay, normally I don't like to do very lengthy derivations like this, although I think Thursday we had a little fun with it. But I think for these 1D equations, it is really important to understand where they come from, because I think that kind of helps to interpret the results. Because even after we do all the integration, we do all the simplifying, the equations themselves are still a little bit obtuse, and so they're not the easiest to handle. And so if you kind of understand how we did the derivation, where each of these terms come from, it'll help you interpret what the equation looks like. Okay. And I think that's especially important for equations like this, and for Navier-Stokes too, because the thing with these equations, these really complicated PDEs, it's really kind of impossible to solve them by hand. And so for these equations, you kind of have to rely on computer software to help you solve a lot of these. And so in those situations, I think it's especially important to really understand what your equation is, where it came from, and what do each of the terms mean. And so that's why I'm kind of spending a lot of the time doing this derivation. Okay. Okay, so any questions on any of this so far? Okay, all right, so let's go ahead and continue on with our momentum derivation. Okay. And so our momentum equation, let me just write it in differential form. Okay. We have partial uz partial t plus uz partial uz partial z plus ur partial uz partial r, okay, plus 1 over rho partial p partial z, okay, is equal to nu over r partial r of r partial uz partial r, okay, plus nu partial squared uz partial z squared. Okay. And so that's our full, I mean, we've already kind of applied some assumptions here to cancel out some of the terms, specifically the terms that depend on theta. But these are all the terms that are remaining after that. Okay. And so this is basically just straight up, you know, Navier-Stokes and cylindrical coordinates. And so we haven't done any integrating yet. Okay. And so just like we did with conservation of mass, you know, we are kind of right in the middle of taking each of these terms individually and integrating their values. Okay. All right. But we're already about halfway done. So we've already done the unsteady term, and we've already done these ones. Okay. These are the convection terms. And so I'm not crossing them out because we're canceling them. I'm crossing them out because we had already done those integrals. Okay. Right. So I'm going to focus on the last three terms that we haven't done here. So they're going to be pressure, viscous term 1, and viscous term 2. Okay. And so if you want to stay consistent with the numbering we had last time, this is going to be integral 4. This one's going to be integral 5. And this one's going to be integral 6. Okay. All right, so let's go ahead and pick up where we left off now. So let's start with integral 4. All right, so integral 4, this is the pressure term. Okay. And so for the pressure term, you know, we have to make one assumption here to make our integration a little bit easier. And so we're going to assume that the pressure is uniform throughout the cross section. Okay. And so all that means is that, you know, if I were to draw kind of a cross-sectional slice, okay, so here's our vessel, and, you know, here is a slice, right? And so we're kind of taking our, you know, taking a plane here and slicing it. Okay, so we have our little slice of blood vessel bologna. Right, and so all I'm doing here is I'm just taking that slice and viewing it from the front, and so you can have a front-on view of that cross section. All this assumption basically means is that this entire cross section here should be at the same pressure. Okay. Now the pressure is going to vary if you move on different locations on the center line, but if you're on the same point on the center line, you know, the pressure is going to be the same throughout. Okay. This is a very reasonable assumption. So even if you don't make it explicitly, you know, and you'll see this when you run your simulations in SimVascular 2, you know, it's very common for a cross section to have, you know, a very uniform pressure, mostly because the blood vessels are so much longer than they are wide, and so because the cross sections are relatively small, this is very reasonable. So this is not really a stretch at all, but we have to make it just to make the mathematics a little bit simpler. Okay. And so integral 4, in you know, when we write out the mathematics for it, we have 2 pi integral from 0 to big R of 1 over rho partial p partial z r dr. Okay. Okay. And so under this assumption, this integral becomes super easy to compute because all of these quantities here do not depend on R. because they're uniform across the cross section, right? So same thing for the density rho. And so, the density is not going to change in a cross section. And so since they don't depend on R, we can just pull them right out of the integral. And so if we have 1 over rho partial P, I can write partial Z, okay? And then we have 2 pi integral from 0 to big R of R dr, okay? If you evaluate this, what's left in this integral, so you can even do this in your head. You're going to have big R squared divided by 2, right? So you have integral of regular R, and so you integrate that, you get R squared over 2. You plug in the integration bound, you get big R squared over 2 minus 0, okay? And so you have big R squared divided by 2. The 2's are going to cancel out here, and you have pi big R squared, right? And what does pi big R squared look like? Assuming that our blood vessel here is circular, pi R squared is just going to be the area. Okay? Right, and so if we go ahead and plug that in, and then so that integral becomes simply A divided by rho partial P partial Z. Okay? So this is the result of integral 4. So thankfully, this one's much easier to deal with than the other ones. Okay? And it's nice, we actually get the area out here. So the area is something that we want to come out of these equations. So that's good. Okay. All right. Any questions on this? Okay. All right. So let's go ahead and keep going. Oh, Zoom people, I'm not sure if the mic is on. I never know if the mic is on in this classroom. So if you've been asking questions, I apologize. But just drop something in the chat. Just say like, hey, in the chat, and then that'll make me pause, and then you can type your question out. So so I never know if the speakers are on in this room. Okay. All right, so let's do integral 5. So integral 5 is one of the viscous terms. And so this is a term that has viscosity in front. Okay. Okay, and so this integral here is 2 pi integral from 0 to big R of nu divided by little r partial r of r partial uz partial r r dr. So a little bit more of an involved integral here, but also not too bad. Okay. We've done the worst of the integration already. So integrals 4, 5, and 6 are going to be much easier to do. Okay, so let's go ahead and work on this integral. And so right away we see that we have an r in front here. We have an r in the denominator, and so these two are going to cancel out. Okay. We can't touch the r that's inside the derivative here because it's inside the derivative. And so, we can't touch that one, but we can work with the ones on the outside. Okay. And so those two are going to cancel out. We have the kinematic viscosity here, nu. And so that is a constant. We're going to assume that that's not going to change. And so since it's a constant, we can pull it out of the integral. Okay. And so what we have from there is we have 2 pi nu integral from 0 to big R partial r of r partial uz partial r dr. Okay. All right. And so we saw integrals like this last week, and so we have it. We see that we have a dr on top, right? We have partial r on the bottom, but it's the same. It's kind of the same thing as dr. Okay, and so these two quantities are going to cancel out, and so all that we're left with is integral from 0 to big R. So I'm going to change this partial up top here to a d, just to emphasize that it's a perfect differential here. Okay, so we have integral of dr partial uz partial r. Okay. And so the nice thing here is this is a perfect differential. Okay. And we know that when we integrate perfect differentials, all we should get is just whatever's inside the d. Okay. And so what's inside the d here is r partial uz partial r. Okay. And we're going to evaluate this from 0 to big R. And so you can almost think of it like, the integral is canceling out with the perfect differential. Okay, so when you see that kind of d by itself, then that's going to cancel out with the integral. Okay, so it's kind of like the same thing as like if you're multiplying and dividing by the same number. Okay, integration and derivatives, in this case, a perfect differential, they're inverse operations. And so when you apply those inverse operations, to each other, they're just simply going to cancel out. Okay, so let's go ahead and evaluate this at the bounds. So we have a big R and partial uz, partial r, evaluated at r is equal to r, okay, minus 0 times partial uz, partial r, evaluated at r is equal to 0, okay? And so we're just taking the result of our integral here and applying the bounds to it. Of course, the second term is going to go away because we have 0 multiplied by something. And so all we're left with is this guy right there. Okay. And so this box term, this is the result of integral 5. Or excuse me, not that by itself, but we also have a 2 pi nu. I forgot about that. All right, so the actual result of integral 5 is 2 pi nu r times partial uz partial r, evaluated at r is equal to r. So this is the result of integral 5. Thank you. Thank you for catching that. Yeah. Mm-hmm. Right. So not the most satisfying expression yet because we still have this kind of partial derivative there. But we'll deal with that in a second. And so if you remember from integrals 2 and 3, there was also a uz that was in there as well. And so we'll kind of deal with all of those at the same time. Okay? But for now, this is kind of as far as we can take it. Okay. Any questions on this integral here? Okay. All right. And so last but not least, we have integral 6. This is another fairly straightforward one. So integral 6 here is 2 pi integral from 0 to big R of nu partial squared uz partial z squared r dr. Okay. Time for more mathematical sacrilege, and so we're going to take the derivative with respect to z. Because it doesn't depend on r, we're going to pull that out of the integral, and same thing with the nu. And so the nu here, we're going to pull that out. Okay. And so we have nu partial squared partial z squared. Okay. I'm going to pull the 2 pi in because it kind of helps us with the integral a little bit. And so we have integral from 0 to big R of 2 pi uz r dr. Okay. The reason I pulled the 2 pi into the integral here is that this guy should look familiar because this is exactly our formula for the flow, right? And so we take the velocity in the z direction, we integrate it over the cross section. So we take 2 pi times that, integrate that between 0 and r, and that gives us the flow. Okay. And so the result of integral 6 is equal to nu partial squared q partial z squared. Okay. And so we finally evaluated all 6 of the integrals. And so let's go ahead and put all 6 of them together. like we're summoning Voltron or something. Get partial q partial t plus 2 pi integral, or excuse me, 2 pi partial z of integral from 0 to big R of uz squared r dr, okay, plus a over rho partial p partial z is equal to 2 pi nu r partial uz partial r, evaluate at r is equal to big R, plus nu partial squared q partial z squared. Okay. And just so that you can keep track of where each of these came from, this first term right here, this came from integral 1. Okay. This term right here came as a result of integral 2 plus integral 3. Okay. So remember, we got the same thing for both of those. And so we just added them together. Okay. This is the result of integral 4, right? So that's the first one we did today. This one right here was a result of integral 5. Of course, this last one is a result of integral 6. Okay. And so that's how we got each of these terms here in this expression. So we kind of reduced the amount of terms, so we have 5 instead of 6, which is an improvement. But we're not quite there yet in having this be something that we can actually use. Okay? But it's a good point. It's a good start. So we've done quite a bit of work to get to this point. There's just kind of a few loose ends that we have to tie. Okay? All right. So any questions on how we got to this point here? People are still writing stuff down, so I'll pause for a second. Okay. All right. So this is a good point here, and so we've done most of the integration that we can. Okay. But we have kind of a little bit of a sore spot here. Okay? Remember when we started today and when we started last Thursday, what we said was that the 1D equations should be solvable for two quantities primarily. Okay? Okay. The first quantity is Q, right? And so we should be able to solve for flow rate from these. And the other one was cross-sectional area, right? So Q and A. Okay. If you look at this equation here, we have more than just Q and A here, right? Excluding some of the extra stuff like 2 and pi and the viscosity and the density, right? So we have things like the physical properties and numbers don't count. But even if we exclude those, we have some uninvited guess. Okay. So the most glaring of these is UZ. Okay. So the uninvited guess, UZ. Okay. In fact, you could argue that we were trying to get rid of UZ. Okay. Right, so he's still sticking around, and so we have to do something about him. Okay. And the other guy that's still sticking around is pressure. Okay. All right, so we have to do something about these two uninvited guests. Okay, because in principle, we only have 2 equations, right? So we only have the conservation of mass equation that we went over last time, and we have this one here, right? And so we have 2 equations. That means we should only be able to solve for 2 unknowns, right? And those 2 unknowns that we want are Q and A. And so we have to do something. We have to make some additional assumptions in order to get rid of these guesses. Okay. Because if we don't provide those additional assumptions, then we're kind of stuck right now, right? And so, that's going to be the next step. So first we'll deal with UZ. That one's a little bit more complicated to deal with. Then we'll deal with pressure. The pressure's a bit easier. Okay. And so the main way that we're going to get rid of UZ, first let's talk about what UZ is. Okay. Okay. UZ, in this case, is just a function of r, and so it's a function of radius. This describes the velocity profile inside a single cross section. Okay. If you remember, when we did our review of fluids, I know I kind of keep coming back to that week, but that's probably one thing that we'll keep referring back to. Then the UZ is what we solved for when we solved our Navier-Stokes equation. Okay. Granted, we had to assume a lot of things like rigid walls, but that was the UZ. Okay. And so visually, it looks something like this. And so for a typical blood vessel, what you have for UZ is a parabolic profile. Right, so typical UZ of R looks something like that. So that basically tells us that the velocity is going to be maximum at the center line of the vessel, and then it's going to go down to 0 at the walls. Okay. And this is the result that we got when we assumed rigid walls. And so if you can assume rigid walls, you can solve for UZ no problem. Okay. And so for rigid walls, you get a parabolic profile. Okay. The issue right now is that because we have deformable walls, or in other words, the walls are be moving, we don't actually know what UZ is going to look like. Okay. But we have to make an assumption in order for us to kind of move forward, because otherwise we're kind of stuck because we don't have enough equations to actually solve for UZ. Okay. And so to kind of break this gridlock, what we're going to do is we're going to say, we're going to take UZ and we're going to assume that we know what the profile looks like. Okay? Because if we can assume the shape of UZ, then that kind of helps us eliminate it. So that'll basically provide one more equation that we can use to kind of eliminate it from our momentum. Okay. And and so there's lots of options. And so there are a lot of different ways that you can assume. Okay. And so in the notes that I have, just kind of for the sake of brevity, I only have one such assumption. But if you go into the course reader, the course reader that I posted for the class, they go into a fairly deep derivation of how you can assume kind of a generic profile. I try to say generic and general at the same time, and it came out as general. It sounds like some guy's name. Okay, but for the class and for the notes that I have, we're going to assume kind of the simplest profile that we can, which is exactly this one right here. Okay. Okay, so let's go ahead and move forward by assuming that the velocity profile is parabolic. Okay. And so this might seem like a stretch, because the parabolic profile that we got, that was assuming rigid walls. And so here in the 1D equations, we don't have rigid walls. And so, this might seem like a stretch. But even in the case when you have deformable walls, the profile still looks roughly parabolic. It's not quite the same, but it is still it's still close enough. Okay, so we'll actually revisit this near the very end of the class when we talk about deformable. We'll talk a lot of details about what the profile looks like for deformable walls, and you'll see that when we plot some of them, they actually do still look fairly parabolic in a lot of cases. And so this is this might seem like it's a stretch, but it's still fairly reasonable for most cases. Okay. And so let's kind of recall our results for UZ of R in a rigid wall case. Okay. And so I'm just going to skip straight ahead to the solution. And so, if you want to see how I got the solution from Navier-Stokes, we did that kind of in week 3 of the semester. But, the result that we got was the following function. So we said that UZ of R is equal to 1 over 4 mu dp dz times r squared minus big R squared. Okay. And so here you can see we have the parabolic profile. So the parabolic profile is given by the fact that we have a little r squared right here. Oops. Right. And so this little r squared, that's the parabolic part of this parabolic profile. Okay. What we also had, based on this velocity profile, we had an expression for the flow rate. Right? And so the flow rate in a cylindrical vessel was given by minus pi big R to the 4th divided by 8 mu times dp dz. All right. And so that was just a result of taking the profile above and then just integrating it across the cross section. So that's the function that we obtained. Okay. And so before we kind of plug this back into our our 1D equations, I want to manipulate this a little bit because right now our UZ here depends on dp dz, which is fine. There's nothing wrong with it. But remember, pressure was also something we were trying to get rid of as well. So let's see if we can manipulate these equations to get rid of dp dz. Okay. Okay. All right, and to do that, we're going to use the second equation that I have here, which is Q. So Q here also has dp dz, and so let's solve for dp dz from the Q. Okay, and so from the second equation, okay, what we have is dp dz is equal to minus 8q mu, right, divided by pi r to the 4th, right? Okay. Let me do one more thing here, just because we're also interested in solving for area, and so I'm going to take the bottom here and note the fact that the bottom can be rewritten as pi r to the squared times r squared. Okay. Pi r squared here is just the area. And so let me go ahead and rewrite this as minus 8q mu divided by a r squared. Okay. So now let's take this expression and plug it back into UZ. Okay. And so if we do that, we have UZ of R is equal to 1 over 4 mu times minus 8q mu divided by AR squared multiplied by little r squared minus big R squared. All right. So let's go ahead and cancel some terms. And so immediately what you should see is that we have a mu up top and a mu on the bottom. Okay. And so those two terms are going to cancel out. We also have an 8 up top and a 4 on the bottom. Okay, so the 4 is going to cancel out, and the 8 is going to become a 2, right? So we just have 8 divided by 4, which is just 2, right? And this negative I'm just going to distribute in through the parentheses. Okay. All right. And so from that, we have the following expression for UZ. And so UZ is here is going to be 2q divided by AR squared multiplied by big R squared minus little r squared. Okay. And so through the assumption of a parabolic profile, we now have something that we can plug back into the 1D equations. Okay. Specifically, we have two integrals here that we can plug them into. And so the first integral that we have is the combined integral of 2 plus 3. Okay. Also, the other integral that still had UZ was integral 5. Okay. And so we're going to see what happens when we plug this into those, we plug into those integrals. All right. Any questions on any of this? Okay. All right, so let's go ahead and plug this back into integrals 2 and 3. Right, so remember this is our combined integral. And so that integral was given by 2 pi partial z integral from 0 to big R of uz squared r dr. Okay. So let's go ahead and plug in this expression for uz into here. Okay. And so if we do that, we have 2 pi partial z integral from 0 to big R of 2q divided by a r squared, quantity squared, multiplied by big R squared minus little r squared squared r dr. Okay. All right. So unfortunately, there's no easy way to do this, and so we're gonna have to do some foiling. We're gonna have to do some integrating, and so it's there's kind of just no way around it. But at least we can move forward, right? And so it's kind of a pain in the ass, but at least with that pain in the ass, we can actually step forward, which is nice. Okay. Okay. And so let me do this. And so let's first let's take this term. Let's leave that there actually. Sorry about that. So that depends on z. So we can't pull that out of the derivative. And so let's just go ahead and start foiling this. Okay. Okay, and so if we FOIL that term, we have 2 pi partial z of integral 0 to big R, okay, of 2q divided by a r squared, quantity squared. Okay, we perform that FOIL. And I'm also going to take the little r and bring it in as well. And that's going to be big R to the 4th times little r minus 2r squared little r cubed, okay, plus little r to the 5th, okay, dr. Let's go ahead and evaluate this integral. We don't have to worry about the 2q 2q over ar squared because that doesn't depend on little r. Okay. Right. And so if we perform that integral, what we get is, I'm going to go ahead and plug in the integration bounds too, because one of them is 0, and so that's going to cancel out a lot of the terms. And so if we do that, we have r to the 6th divided by 2 minus r to the 6th divided by 2. Okay. And so that's the middle term. And then the last term is we have an r to the 6th divided by 6. Okay. All right, so we have an r to the 6th divided by 2. We have a minus r to the 6th divided by 2, and so these two terms are going to cancel out. Okay. And so let's go ahead and expand out the square term. And so if we expand out this square term, we're going to have a 4. We're going to have a 4q squared divided by a squared r to the 4th multiplied by r to the 6th divided by 6. Right. Okay. And so we're going to have a lot of these terms. We're going to have a lot of these terms cancel out. Okay. And so we have an r to the 4th here. And so that's going to cancel out with this r to the 6th. And so we're just going to have r squared up top. Okay. We have this 4 is going to cancel out with the 6. And so we're going to have 2 over 3. Okay. And so if we do that, we have 2 pi partial z of 2q squared r squared divided by 3a squared. Right. Okay. We're almost done. And so let's take this 2 pi, because it doesn't depend on z, we kind of move it, we can move it inside and outside of the derivative as much as we please. Okay. And so we can go ahead and move it in. And what you'll notice is that we have a pi coming in from the outside and an r squared on the inside, right? Okay. And so we know what pi r squared is. So pi r squared is going to be equal to a. And so those are going to combine and get area on top. Okay. And since we're going to get an area on top, oops, since we have an area on top, that's going to cancel out with one of the areas on the bottom. Okay. And of course, we can bring the 2 inside as well. And so the result of this, finally, is we have partial z of 4 q squared divided by 3a. Right? So it was a long journey to get here. You know, this was the most difficult integral to work with, but we end up with a very clean expression here. And so we end up with something that just has q, just has a, has a couple numbers floating around, but it also has partial z. Okay, and so this was the result of integrals 2 and integrals 3 together. Okay. All right. So let me give you some context behind this term. And so, you know, this was obviously the term that we did the most work on, and that's not by mistake. And so if you kind of look back to the original momentum equation and where these 2 terms came from, these were the terms that were associated with convection. Okay, and so convection, if you kind of remember from your fluids class, you know, involves kind of it's basically the transport of momentum along a flowing fluid. It's the notorious term within Navier-Stokes that makes it, you know, that's the term that makes it impossible to solve. This is the convection term. And so anytime that you're doing any kind of work with convection, you know, you're always in for a battle, because convection is always, you know, always very, very difficult to solve. Okay. And in the end, we get something that, you know, even though it looks clean, it's actually very difficult to solve still too, because we have q squared. We have q squared inside a differential equation, and so that's already going to be really challenging. And then we have divide by a, and so a is in the denominator inside a differential equation. And so, you know, even though we did a ton of work in trying to solve this, it's still really, really difficult to actually solve. And so, you know, I know when I put it like that, it's a little bit deflating, especially after all the work that we did, but that's just the nature of convection. And so that's why, you know, there's some society out there, I don't even know who it is, but, you know, they said if you can solve Navier-Stokes with the convection term in an analytical sense, then you get $1 million. You know, and, you know, for anyone that works in the field, you know, you would honestly think $1 million is not enough to solve this problem, because it's that difficult, right? And so even in this attempt to try to simplify this, you know, with integration, you know, we still end up with something that's, you know, very, very difficult to solve. But that's just the nature of what convection is, and that's what makes fluid mechanics so difficult. But it also makes it really cool. And so, you know, give and take, I guess. Okay. Any questions on this? Okay. All right. So that's integral 2 and 3. And so let's not forget our lost child. And so, you know, we can't forget integral 5. Okay. So integral 5 is a lot easier. So, you know, we're not going to spend a lot of time on this. And so remember, the result of integral 5 was 2 pi times r times partial uz partial r, evaluated at little r is equal to big R. Okay. All right. And so all we have to do here is now that we have an expression for uz, we can just plug in uz here. We're going to plug in uz there, and then of course we're going to take the derivative with respect to r. Okay. And so if we do that, we get 2 pi nu times big R. Right. And if we plug in for uz there, we take the derivative, we get a minus 2q divided by ar squared multiplied by 2 times big R. Because we take the derivative with respect to r, and then we plug in anywhere we see a little r, we plug in a big R. Okay. Right. And so of course, you know, all these r's are going to cancel out, because if we have an r up top, it's going to cancel out with the r squared. We have another r up top that's going to cancel out with the last remaining r. Okay. And so if we plug everything in, we get a minus 8 pi nu q over a. Okay. All right. And so we're finally ready to go. Okay. And so we can finally assemble the Infinity Gauntlet, Voltron, whatever pop culture reference that you want to make there. Okay. And so now that we've substituted for UZ, that's going to be the bulk of our work. And so we can finally assemble the 1D equations, in their final form. Okay. No more boss music. This is the final form of the boss, I promise. Okay. And so, of course, that's our momentum equation. Okay. So that was the result of all the hard work that we did. And then that is our conservation of mass on the bottom. Okay. And so these are the 1D equations of blood flow. Okay. Under the assumption that you have a parabolic profile. And so, of course, we still have a partial differential equation, quite a complex partial differential equation. I could tell you that it's not as bad as Navier-Stokes, but even I have a hard time believing that. It's still you still can't solve this by hand. You need to do a computer code. But I do have a computer code that is posted, and so I do want to show you that before we end today. Or we might not have time, so maybe I'll do it kind of first thing next time. Yeah.
It's the A over P,
A over P,
right?
or which one? Oh, it's A over rho. I'm sorry. Yeah. So the rho, this is a density right here. Yeah. Thank you. So this rho here, this is density. Yeah, the pressure is in the derivative. Okay. Right. So these are the 1D equations, but probably some of you are like, wait a minute, we only took care of UZ, right? So there's one other guy that we had to take care of, which was the pressure, right? So what about that guy? And so it seems like we still have some unfinished business. Well, luckily for us, the pressure is a lot easier to deal with. And so we don't actually have to modify these equations. For the pressure, we're just going to add one additional equation, okay? Okay. And the equation that we're going to add, it belongs to a certain category of equations. And basically what these equations are going to do is that they're going to relate the pressure inside a vessel to its cross-sectional area. Okay. And these kinds of equations have a special name. And so you might have some of you actually might have seen some of these equations before. If you took a strength of materials class or an advanced strength of materials, these are called constitutive equations. And so constitutive equations are, they're a staple in kind of advanced strength of materials. And so they make some relationship between, usually some geometric quantity and then some dynamic quantity. So either like a pressure or like a stress or something like that. Okay. So they're a lot more common in there. And, I can't say I'm enough of an expert to really comment anymore on that. But if you are going to go pursue a lot more strength of material science, then constitutive models, constitutive equations, probably something you're very familiar with. Okay, and so we're going to borrow a little bit of that to help us complete these equations. Okay. Right. And so there are two that are commonly used in the 1D equations, and they're named after the people that that discovered them. Right, and so the first equation that we have is Kasab, and so his equation says that the pressure minus some reference pressure is equal to the Young's modulus in the vessel wall multiplied by HO, which is a reference, which is the thickness of the vessel wall, divided by RO, multiplied by the area divided by AO minus 1. All right, and so basically what you would do is you would take this equation, solve it for P, okay, and then you can plug it directly into the 1D equations up there. Okay, so this is the additional equation that you would need to basically eliminate pressure from the whole system. Okay. Although traditionally, it's if you look into some of the codes for the 1D code for the 1D equations, it's not usually used like that. So these equations, they're thought of as like an additional equation to solve alongside it. Okay. Okay. So let me go ahead and define these terms just so that you know what they are. So P0, this is what's known as a reference pressure. Okay. And so it's the pressure inside the vessel at some kind of reference state. And so usually they take a flow-free state. And so if there's no flow in the vessel, what does the pressure look like? E here is the Young's modulus. Okay. So Young's modulus, hopefully sounds familiar. So that's a measure of the stiffness of a material. Okay. And that would be the stiffness of the vessel wall itself. Right, we have HO. So HO here is the wall thickness. Okay, so how thick the vessel wall is. We have RO. RO here is the radius of the vessel in the reference state. And so once again, if you were to take the vessel and you were to say that there's no flow and measure the radius, then that would be kind of the reference radius. Okay. And of course, A0 here, just like P0 and R0 up there, this is the cross-sectional area in the reference state. Okay. So the Kasab model is one such constitutive equation that we can use to close our system, or in other words, give us something that we can solve for the pressure. All right. Any questions on any of this so far? Okay. All right, so that's one such model. And the other model is called the Olefson model. And so the Olefson model is actually a two-equation model, and so it has two such equations. And so the left-hand side is similar, so we have P minus P0. And on the right-hand side, we have 4/3 times EH divided by R0, okay? 1 minus square root of A0 divided by A, okay? Where this quantity right here, EH over R0,
actually has another equation for it. Okay? And so EH over R0 is equal to K1 times E to the K2 R0, okay, plus K3. Okay. Where K1, K2, and K3, those are some parameters that you can set in order for you to fit the material. So those are normally determined by experiments, and they're kind of a material by material basis. And so the Olefson model gives you a little bit more customization in terms of what how your constitutive model behaves, but it's still perfectly good. But the Olefson model is more for kind of if you kind of know what you're doing, and you know what to set for K1, K2, K3. Then the Olefson model is good. But for most people that when you're first starting out, the Kasab model is better, just because there's less for you to have to set. Okay. Any questions on this before we do? I think we'll have enough time to at least for you to see what the results look like, and then we'll really kind of talk about it more on Thursday. Okay. All right, so that's all the derivation, and so we spend a lot of time doing that. So let's see how it's actually applied. Okay. All right. And so just like I mentioned before, the 1D equations, even though they are a simplification over Navier-Stokes, they are still a very complicated PDE. And so in order to actually solve them and apply them, you need to write some computer code to actually do it. Okay. And so, actually having you guys write the code for that is way beyond the scope of this course. And so what I did instead was I had a good colleague of mine. He had kind of a good 1D code where he applied it to just a single vessel, and then I'm going to use that vessel to kind of illustrate its purposes. Okay. Okay. And so the example code that we're going to see is my colleague was interested in studying carotid arteries. And so those are the vessels that basically take blood from your heart and go up to your brain. So those are the vessels that are in your neck, basically. Okay. And so he was using the 1D equations to basically study, how the flow and pressure, is propagates within these vessels. Okay. Okay. And so he applied it to a single vessel. Okay. And so since this is a 1D equation, I'm going to draw the vessels as just a single line. Okay. At the inlet to the vessel, we're going to apply a flow rate. Okay. And so this Q in right here, this is going to be our inlet flow. Right. And so think back to when we did our lump parameter models, right? There were times when we applied a flow rate at the inlet. Okay? And so what this describes is this is the amount of flow that's coming into the vessel. Okay. And we also have to supply the area at the inlet. Okay. And actually, let me plot for you what the Q in looks like. And so the Q in looks something like this. Okay. Okay, so it's going to be a time varying waveform, and so it's not going to be constant. Okay. So remember, just like our non-parameter models, we always had a sinusoidal input at the inlet. Okay. This one's going to be a little bit more realistic, and so he didn't use a sine waveform. But what he did was that he actually took his patient and he actually measured what the flow actually looked like in his carotid artery. So he basically did his direct measurements. Okay. And so if you look at the results, it looks something that kind of looks like this. And so it's flat for a little bit, and then it jumps up, and it comes down. It has kind of a wiggle, and it comes back down there. Okay. And so this is a measured waveform in carotid artery. Okay. All right. And so this is a time-dependent waveform. And so, what this means is that when we measure the flows and pressures everywhere else in the artery, they're also going to change with time. And so our solution to 1D equations will also change with time. And that's not surprising because, if you look back at the formulation for our 1D equations, you'll see that we have a time derivative there. And so we have capacity to solve for situations like this. All right. Okay. And so let's look at kind of the first primary result. And so the first primary result that I want to show you is the flow waveform at the inlet and outlet. Okay. Okay. We'll talk about the other result first, but I kind of want to start with this just because we're running a little bit short on time. Okay. All right, so I'm going to go ahead and jump to the Matlab code. So before I do that, are there any questions on this before I switch the screen? Okay, all right, so let's go ahead and switch to the screen. Okay, so here is the code, and so we'll go over kind of the intricacies of the code next time. But let me just go ahead and run it for you. Okay. Busy, busy, busy. Okay, took about 11 seconds. Okay, we'll talk about the pressure next time, but let's look at the flow. Okay, let me go ahead and maximize this. Okay, and so what you're seeing here is the flow waveforms as a function of time. Okay, and we're viewing it at two locations. So one is at the inlet, and the other is at the outlet. Okay, and so the blue here is the inlet one, and so that's what we're putting right into the model. So that's the waveform that I showed you. Okay, and the red one is the flow at the outlet. Notice how they're different. And so if this were a rigid wall simulation, and so if the walls were not able to move, these two quantities should be right on top of each other, because whatever you put in to a rigid model should come out. Okay, so that's conservation of mass. The fact that we don't have exact overlap shows that we have deformable walls. And so there are times when we have a gap between the blue and the red, and so that means that flow is being stored into the vessel. So the vessel is inflating, storing flow. And then times when the red is above the blue, that's when the vessel is deflating, right? So it's basically being squeezed, and then all that excess flow that was stored before is being pushed out the outlet. And so you have more outflow than you do inflow, okay? And so this is really cool. And so, we did a lot of work to get here over our lump parameter models and over our rigid walls, but we are able to see some pretty realistic behavior from this model. All right, any final questions on this before we wrap it up for today? Okay, all right, so next time on Thursday, we'll pick up this code again, and then I'll kind of talk a bit more detail about it. But there are a lot of really cool behaviors that you could see. A lot of the behaviors that we talked about in the arterial biomechanics section, you'll actually get to see it in practice here. So hope you guys look forward to it. All right, so have a great afternoon, everyone. Thank you again for tuning in as usual. And thank you everyone for coming here in person. And I'll see you guys on Thursday.
Hey, sure.
So I got to this part for like problem or two,
Mhm.
but this is way off from what you had. Like the answer for the
Let's let me pull